In this video, I want to find the derivative of e to the x using the limit definition. So in other words, finding the limit as h approaches 0 of f of x plus h minus f of x all over h. So the first thing to do is to find f of x plus h, and for every x, I'm going to replace it with x plus h minus e to the x all over h. Next, I'm going to break up e to the x plus h as e to the x times e to the h, and then we have minus e to the x all over h. I have a factor of e to the x in both terms, so I'm going to pull that out. This is going to be limit as h approaches 0, e to the x times the quantity e to the h minus 1 all over h. And in this case, because we're looking at a limit as h approaches 0, anything that is not h is going to be treated as a constant. So, in other words, e to the x depends on x, which is not h, so it's going to be a constant that we could just pull out in front. Because whenever we're looking at a limit of a constant times a function, we can pull out the constant and leave the function inside. So what we'll do that, we're going to have e to the x times the limit as h approaches 0 of e to the h minus 1 over h. At this point, we reach the critical step. So we can take two different routes. One is to do L'Hopital's rule, or two, do a couple substitutions and get the limit. For the purpose of this video, I don't want to spend too much time on L'Hopital's rule, but I will talk about it briefly. So the reason I can use L'Hopital's rule is I get an indeterminate form, which in this case is 0 over 0. So then I could just take the derivative of the top, so the derivative of e to the h minus 1. E to the h is its own derivative. The 1 is a constant, so the derivative of that is 0. And then h, the derivative of that is just 1. So this limit is just going to be 1, because e to the 0 is 1. And so my limit is e to the x. So from there, we say that the derivative of e to the x is e to the x. Okay. So now let's go back and let's actually use a different way. So let's start with this line right here. And let's ignore the L'Hopital's route. So I'm going to have e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. I'm going to make a substitution. I'm going to let n equal e to the h minus 1. So this top part here is going to be replaced with n. And that leaves h in the denominator. So I want to solve for h, and n equals e to the h minus 1. So I'm going to add 1 to both sides. And then I'm going to take the natural log of both sides. ln of e to the h can just be simplified as h. And I'm just going to switch the n plus 1 as 1 plus n, just for convenience. Okay, so h then is going to be replaced with ln of 1 plus n. So let's change that. So I'll have, let's see, e to the x times limit as, okay, now we have, instead of h approaching 0, we have everything in terms of n. So let's make a substitution here. So let's see. H approaches 0, we said. So that means e to the h minus 1 is going to approach e to the 0 minus 1, which approaches 1 minus 1, which is 0. And e to the h minus 1, we said, is n. Okay, from over here. So now we'll have n approaching 0. The numerator is n, the denominator is ln of 1 plus n. And here, if I plug in 0 for n, I get 0 over 0. So I'm going to do a little bit more work. I'm going to multiply the top and the bottom by 1 over n. These are going to cancel. I'm left with e to the x times limit as n approaches 0 of 1 over n times natural log of 1 plus n. The 1 over n is going to be the exponent of the 1 plus n here. And just to review, if we have k times natural log of n, that's the same thing as natural log of n to the k. So let's rewrite that. I'm going to have e to the x times limit as n approaches 0 of 1 over ln of 1 plus n to the 1 over n. I'm going to make a substitution now. So I'm going to let u equal 1 over n. So n will just be 1 over u. So you just take the reciprocal of both sides here. We said that n approaches 0. So 1 over n is approaching 1 over 0, which is really infinity. Okay. And we're going to say positive infinity since we're dealing with natural log. Right, and natural log is defined for x greater than 0. So there's nothing happening, on this side right here. So we will use n approaching, or 1 over n approaching positive infinity. And now we're going to make some substitutions. So n is going to be replaced with 1 over u. 1 over n is going to be replaced with u. And then this thing is going to be replaced with u approaching infinity. Right? Because 1 over n approaches infinity. 1 over n is u. So let's make those changes. I have e to the x times limit as u approaches infinity, 1 over ln of 1 plus 1 over u to the u. Okay, now I can pull out the natural log. So just to review, if I have a limit as x approaches a of f of g of x, if f is continuous at a, I can bring it outside and compose it with limit as x approaches a of g of x. Here the f of x is going to be the natural log, and then g is just a 1 plus 1 over u, raise it to the u. So it's the whole thing, raise it to the u. So, and here f is continuous at infinity because we said, here as x gets bigger and bigger, it's continuous there. goes on forever because the domain is 0 to infinity. Okay, so I'm going to rewrite this as e to the x times the limit. Sorry, before the limit, we need to do the natural log. We'll do this, 1 over the natural log of the limit as u approaches infinity of 1 plus 1 over u, and that thing raise it to the u, like that. So this limit is e, so I'm left with e to the x times 1 over ln of e, and ln of e is just 1, so I'm left with e to the x. So we proved that the derivative of e to the x is equal to e to the x.